In this lecture, we're going to cover 2.6, and we're going to explain how chemical properties of water make life possible. 2.7, we're going to describe the pH scale and the role of buffers in body fluids. We're going to do 2.8, describe the functional roles of inorganic and organic compounds. And 2.9, we're going to discuss the structures and functions of carbohydrates. First of all, water is an essential reactant in chemical reactions of living systems. There are three key properties of water. Number one, it's the essential reactant in living systems. Number two, water has a very high heat capacity. That means it tends to resist change. So what happens is, when it takes a while for water to boil, between 10 and 20 minutes, depending on the heat of the stove. But once it gets hot, it holds its heat. It resists change. It takes time. Water takes a while to freeze, but once it's frozen, it holds the cold. And finally, the last thing is water is an excellent solvent. It's known as the universal solvent. What makes water so amazing is it's a polar molecule. When we have a solution, the definition of a solution is a mixture of a fluid. The fluid is a solvent, and then dissolved solutes. So when we put something like sugar in water, sugar in tea, sugar in coffee, the water, tea, or coffee is a solvent, and the sugar is the solute. There's a thing that happens called dissociation or ionization, and that occurs when the ionic compounds break apart into their charged ions in the water. An organic molecule is soluble when it contains polar covalent bonds. This is the image of the water molecule, and you can say it's a polar molecule. It has a negative pole and a positive pole, or a negative side and a positive side. Again, this is one of the reasons why it has all its unique properties. Again, here's another picture of salt in water, water being the solvent and salt being the solute, and you can see how the sodium and the chloride break down into its component ions and dissolve in the water. This is an example of the glucose molecule dissolving in the water. Now, let's go to pH 2.7. A hydrogen atom that loses its electron becomes a hydrogen ion, or H+. H+ is very reactive and can break apart many important bonds or chemical bonding. So the concentration of H+ in the body must be narrowly maintained within a normal pH for the human body. So the pH scale runs from 0 to 14, 7 being neutral. A solution with a pH less than 7 is acidic, whereas a solution above 7 or greater than 7 is alkaline or basic. This is an illustration of the pH scale. You can see that pure water is neutral at 7. Urine can run from acidic, neutral to basic or alkaline. You can see that stomach acid, hydrochloric acid, is the most acidic with a pH of 1. The lower the pH, the more acidic. If you also observe, ocean water is basic or alkaline, and oven cleaner is the strongest base at a pH of 14. So the higher the number, the more basic it is. Remember that acids, bases, and salts are inorganic compounds, and they dissociate in water into ionic forms. Remember that acids always dissociate into a cation that is always H+. The stronger the acid, the more dissociation occurs. That means there's more free hydrogen ion present, and that means the lower the pH. That is what makes up a strong acid. With bases, they dissociate into an anion that is OH negative. The stronger the base, the more dissociation occurs. So there is less free hydrogen ion, or H+, so the pH is higher and that's a strong base. Salts are an ionic compound, and they dissociate into a cation that is never H plus and an anion that is never OH negative. It's always table salt, NaCl. So the solution dissociates into sodium plus or chlorine negative. The dissociation of salts makes a solution. It can be slightly acidic or slightly basic. They are examples of electrolytes, and they do conduct an electrical current. Buffer systems are very important in the human body. They help us maintain a pH in a homeostatic range of 7.35 to 7.45. It's a very narrow range. And what they do is they stabilize the pH by taking the hydrogen ion or cation out of solution or dropping the hydrogen ion into solution. Now we go to the organic molecules. And there are 4 or 5 basic organic molecules: carbohydrates, lipids, proteins, nucleic acids, and ATP. We're going to cover section 2.9, carbohydrates, today. They're organic compounds with carbon, hydrogen, and oxygen in a ratio near 1 to 2 to 1. 1 carbon to 2 hydrogens to 1 oxygen. Some people call it carbon water or carbon H2O. They include sugar and starches. They're a good source of energy, and there's 3 major types: monosaccharides, disaccharides, and polysaccharides. Monosaccharides are simple sugars. Mono means one, saccharide means sugar. They're building blocks for larger carbohydrates, and they are easily dissolved in water. Glucose is the most important energy source in the body. You can take a look at the structure of glucose here. Next are disaccharides and polysaccharides. Disaccharides, di means 2, saccharide means sugar. They include sucrose, maltose, and lactose. They're 2 monosaccharides linked by covalent bonds. And polysaccharides are, poly means many, saccharide means sugar, and they include starch and glycogen. There are multiple monosaccharides or disaccharides linked by covalent bonds. They are broken through hydrolysis, or they are formed through dehydration synthesis.